Hi everyone, my name's Eric Tarr. I'm coming to you today from Nashville, Tennessee. I appreciate your interest in my presentation. I also want to thank the conference organizers for giving me this opportunity. Today I'm going to be discussing a software toolkit available for audio developers that performs automated analog circuit modeling. When I set out to create this toolkit, I wanted to create something for everyone that made it possible for developers to take advantage of analog modeling in their own audio plugins, apps, or really any C++ software that needs to process audio in real time. This toolkit is called point-to-point modeling. It's intended for audio software development, but we also think there are aspects of it that will be great in education and as a creative tool just in music production, because we've released a plugin that's called the Analog Circuit Factory that's built on top of point-to-point modeling that you can load up and run in real time in any digital audio workstation. So there are several different versions of the library to know about. The primary one is C++, intended for software developers like you who are writing your own plugins and apps. We're also working on compiling this for Linux, so it could be used in the future on embedded processors. Next up, we have the plugin, the Analog Circuit Factory. This plugin is set up to read in very simple XML text files that represent the schematic information of circuits. The plugin will read in these XML files, automatically perform the circuit modeling, and then apply that DSP to whatever signals are running through the plugin in your DAW. We've included an enormous collection of these XML files for you to use. These examples can also be edited and modified if you want to see how that might change the processing in your DAW. You can also write these XML files from scratch for whatever circuits you'd like to be able to test. Next up, we have a Python version. This is intended more for prototyping because it's not going to perform real-time processing. But what we have done with the Python version is giving you some example test scripts that will perform all the common analyses, like looking at the waveform or oscilloscope for a signal running through the circuit, the frequency response, the harmonic distortion, those sorts of things. We've set that up for you straight away to make it easy to put in your own circuits and then be able to figure out how they're going to ultimately perform. Also with the Python version, we made it possible to read in your XML files and automatically output C++ code that you can then copy and paste into your own plugins without having to rewrite anything. Next up, we have the MATLAB version. This is again meant for prototyping. We think that this is a great way in commercial settings to be able to quickly write simple code that you can test and see how a circuit is going to perform. We also think it's going to be useful in educational settings for teaching. All right, what happens if we change this type of component or element of a circuit and see the effect that it has on the processing? Also with MATLAB, you can write your simple MATLAB code and then using a built-in function that we provide, output XML files that you can then load straight away into the Analog Circuit Factory and go from MATLAB prototyping into real-time processing in a plugin with just a click of a button. For the rest of this presentation, what I'm going to do is go through these different versions of the library and show you how quickly and easy it is to get started, but then also the creative potential that you have to open up unlimited possibilities for doing the circuit modeling. So the first thing I'm going to demonstrate for you is actually the Analog Circuit Factory plugin. Here, the XML circuits are loaded up as 500 series rack modules, and you can daisy chain them together right within the plugin. We have the circuits categorized by things like guitar preamps and tone stacks, and hopefully you can see here just the huge collection that's at your disposal to be able to work with. We have a lot of analog EQs that have been modeled if you want to get away from using the same standard digital EQs over and over again. We have lots of guitar pedals that are broken out as well, and analog saturation sections from diodes, transistors, and tubes. Again, these are all XML files that you can load up. So I want to show you what this looks like. So we have a very simple format for you to use. You can name your own circuits or edit the ones that we have for you there. You can edit the component values for things like resistors and all the capacitors that you'd ever want to lay out in your circuit. And then we have potentiometers, and so you can specify things like the direction of the knobs that are automatically going to get attached to these potentiometers in the 500 series rack module. And then I'll also show you here with the diode what kind of parameters you have to adjust. If you want to change things like it being a silicon diode or a germanium diode, you can make a matched pair of diodes or a single diode and edit lots of the characteristics of those things. Also to go along with our XML files, we have a PDF of all the circuit schematics, over 100 of the circuits that are included. We have PDFs for, so you can use this as cross-reference to see some examples, how they're laid out, where we number all the nodes and give you component values to help you get started if you wanted to take these and build off of them to build other circuits. Next, we're going to move on from talking about the audio plugin, which we feel is a very powerful tool for experimentation. And we'll switch gears and talk about the C++ version of the library, which is meant really for the implementation of your real-time audio software. With the commercial version of the C++ library, you get access to this Circuit Examples Pro Juicer project that we've prepared. This is meant to serve as a template for your own audio software, whether you're creating a plugin or also an app. What we've done here is set up everything that you need to do to link the library in. So external files to link, and also set up the header search paths. Then we can open this in Xcode. Here is our Circuit Examples audio processor, highest level of the DSP code for our plugin. What we've added in here is just a single class, an instance of one of the circuits that's included in our library. And we'll just generically call it an effect. But if we wanted to change out the circuit to something completely different, we just need to change the name of it right here. So let's go through and check out the circuits that you can find and be able to either modify or use or take and build your own circuits off of these things. So we have our amp clippers, we have our amp tone stacks, our clipping circuits with diodes. These are all the same circuits that you'll find in the plugin that now you have the C++ versions at your disposal to use and modify. Again, we just go back here and we'll say, let's create the Baxendale 1 effect. And that's all it is, to just build the plugin again, and now you have a completely different circuit that you have running inside of the plugin. It's that easy. Let's take a second now to check out, well, what is a circuit actually made up of? At its core, every circuit effect that we're doing is a circuit model. And that's where all the magic and the DSP happens of the automated circuit solving. Circuit model gets a thing called a circuit layout. This is your schematic information. So how many nodes do we have as part of this circuit? What are the individual circuit elements in here? We're going to create vectors of all these things that we want to pass in. Then we have all the familiar callbacks that we would find for processing buffers of audio, whether it's an input and output or an individual buffer processing an individual sample. We've got to prepare it like a plugin with the sample rate and the buffer size. If we have parameters like potentiometers or variable resistors, we have internal smoothing that's already set up that you can control the number of samples for. And then when you want to actually change the values of the parameters, you set them using a vector right here. So this is where really all the action happens for when you're creating your own circuits, what you need to be aware of and what you need to set. So these circuits are then made up of these individual elements, and you can look at the documentation here in the class implementations to find out which circuit elements are available, and also how you can set the different parameters on them. So again, those go into a circuit model. Lastly, we have a circuit processor, which is our abstract base class that serves as the interface into the library. We have circuits that are implementations then of that circuit processor base class. Here, that's what you would use if you're just trying to create one circuit at a time, where you specify the individual layout for it and pass it into its circuit model. And that's how we would then use the individual circuits. But we also have this thing called a circuit chain that also inherits from a circuit processor. And why is this? It's so that we can create a vector of circuit processors. So if you want to create a chain of arbitrary effects, that could be a bunch of individual circuits together, or also a combination of circuits and other circuit chains that you've made before, you can do that and make this very powerful thing. So meant to be very, very modular. So again, if you just want to get started using it, you go in here, you change the name of your circuit, and then we go in here to prepare to play, like you would normally do in a plugin, and you need to prepare our effect with the sample rate and the block size. And then we go down here to our process block, and we go in here to our loop after we've grabbed our channel data, and then we pass that channel data into our effect, and that's all you need to do in order to get started writing code for the C++ version of the library. I'm going to go ahead and build this example plugin now so we can see it. It's a very basic JUCE plugin with some few knobs. And so if you have these knobs, potentiometers mapped to parameters in your circuit, then they will update that and you can experiment with changing those things. on it. So there you go. That's what you need to do to set up the and get started with the C++ version. We're going to shift gears and talk about MATLAB. The MATLAB version of the point-to-point library is available as a public GitHub repository. So you can use this for prototyping in your own commercial software, or you can use it as an educator and have your students be able to use this as well. They want to learn about how to use circuits and modify them and experiment with them. So if we dig into the repository, at the highest level, we have a number of test scripts that are set up that I'm going to demonstrate for you so you can get an idea just about how easy it is to edit and modify and see the results with different circuits. We have included in MATLAB all the same circuits that you find in C++ and also the Analog Circuit Factory plugin. And so it's just written in MATLAB syntax instead of some other programming language on it. But the same exact structure and architecture to the library is in MATLAB here too. So we have all the files for circuit model and all the different classes for our circuit elements as well. So now let's go back and take a look at the test script and experiment with it. So here I have the Boss Blues driver clipping stage that we're going to play around with. I've set this up as going to be the circuit we're going to analyze. Down here we have these simple flags, these booleans that you can set depending on what type of analysis you want to use. So this is code that's already set up to plot the waveform, the frequency response, the harmonics, and that sort of thing. And you can even go in and change the MATLAB code if you want to say, oh, I want to analyze a different frequency or the number of cycles or some amplitude or even a different type of sine wave or square wave. All those things are easy to modify in MATLAB. So all I'll do is just go ahead and run this, and we'll see two plots will eventually come up. That one is going to be the waveform, and then one is going to be the THD or the harmonic analysis of what happens with it. So over here on the left, we have our cool analog distortion that's coming in. And over here on the right, we see our even and odd harmonics that come from sending a test signal through this particular circuit. And then if we wanted to, we could go back in and change some of the components or element values, change our resistors. We could change the type of diodes, and then go back and run our test script again and see in a matter of seconds, what's the result of swapping out these different kinds of components on our circuit. Another cool thing that we've built into the MATLAB library is the ability to take your MATLAB syntax of a circuit and have it spit out an XML file. So I ran the script this time, which called this function, and it created for us this new XML file that wasn't there before. And this XML file has the same exact formatting that we use with the Analog Circuit Factory plugin. So if you want, you can go from MATLAB, click a button, using your MATLAB Boss Blues driver, have it create this XML file, and load that XML file up in your Analog Circuit Factory plugin, have it running in a matter of seconds in real time. Also with MATLAB, we have the ability to read an XML file. So if you have experimented with a circuit that you've written in XML, you can load it up into MATLAB and have MATLAB use that as part of your test script analysis. Next thing I'm going to show you is a second parameter test script that we have prepared. This is more for circuits where you have a potentiometer or variable resistor that you want to adjust and see what happens when we change some of the different settings and plot like the frequency response for different values on it. So here I have this Baxandall EQ where we have a bass knob and a treble knob. And what I want to do now is run a frequency response analysis where I look at, well, what are these different settings going from the minimum setting of the potentiometer all the way up to the maximum. So I have this loop here of the resistor value going from 0 to 1, and I pass that resistor value in, the new one, each time into this before I do the analysis of the circuit, and then I plot the frequency response each time. So for the circuit, the resistor value in here first is for the bass. That goes along with parameter number 1. Parameter number 2 is treble. And so what I've done is I've set the resistor value of the bass is going to change, and the resistor value of the treble stays the same at 0.5, just its original value. So if I run this again and plot it, now we see the plot that shows us as we adjust this knob, we can get these different frequency responses. And so this is another really powerful way to analyze and make sure that your circuit is functioning properly for all the different range of parameters that you want to put in for any of these variable controls. So that's the basics of getting started with the MATLAB version of the library. Now we're going to shift gears and look at Python. So the purpose of the Python version of the library is for prototyping, just like what we were seeing before with MATLAB. But this was one of our highly requested features, was to make it possible to work in Python because a lot of developers prefer to work there. A cool thing about Python is we can utilize Python bindings, which allow us to call actual C++ code from Python and pass data in that way. And so the static version of the C++ library for point-to-point is actually what we're using to process all the data. And that's why you're seeing these .h and .cpp files within this Jupyter notebook. So what I'm going to demonstrate is here utilizing this test script that we've prepared for you to be able to use. This is very similar to what we were seeing before in MATLAB. Here we have these different sections of code, though, for bringing in specific circuits from different categories, setting up the analyses that we'd like to be able to run, like the waveform, frequency response, THD, and DC sweep. I'm going to assign the circuit here. This is a Baxandall one, but I could swap out that circuit for any of the other ones. And be able to test that. Really the one that's interesting is the frequency response. That shows us that bump down there at low frequencies. And then if we wanted to, we could also look at the total harmonic distortion, which isn't showing any harmonics for this linear circuit, or the DC sweep. So that's a very useful way to be able to go in and analyze specific circuits. We also have this second script that makes it possible for you to modify different parameters for different potentiometers of a circuit. And then we can run this entire script all at once. And what will happen is we'll bring up all four of those plots in one window to see what's happening when we modify parameters. I'm going to switch gears now and show you that with Python, we have this ability to work with XML files. And so if you have an XML file that you have worked on outside of Python, maybe with the Analog Circuit Factory plugin, and then we'd like to move that over and put it inside of C++, we have this automated script for importing an XML file that when you run it, it will output C++ code and put it in a user circuits.h file that then we could take this code and load it up in our plugin and be able to use it without even having to write any more C++ code. In conclusion, I hope you're able to see, with the point-to-point library, we really set out to try to create the complete software toolkit for you as audio software developers who are interested in having analog circuit modeling in your own products. We want to make it as easy as possible for you to get started by providing an enormous collection of over 100 circuits that you'll find the same ones across the entire suite of software tools. Again, we're also giving you the flexibility to enter your own arbitrary circuits into the library to really harness the power of what it has to offer. For more information, please head over to hackaudio.com. I'd love to connect with you over there if you want to reach out and contact us. Thanks again for your interest in my presentation. I hope to hear from you soon. Take care.